In this class, we'll see the convolution properties. The first property is commutative property. Commutative property. x1 of t convolution with x2 of t is same as x2 of t convolution with x1 of t. Okay, so convolution operation is commutative. Then second property is distributive property. Distributive property, that is x1 of t convolution with x2 of t plus x3 of t. Okay, now there are three signals. Okay, see, we are adding x2 of t with x3 of t, then later we are convolving with x1 of t. It is same as x1 of t individually convolving with x2 of t. Okay, then adding the result with x1 of t convolution with x3 of t. x1 of t convolution with x3 of t. This is distributive property. Next, associative property. Associative property. x1 of t convolution with x2 of t convolution with x3 of t is same as x1 of t convolution with x2 of t, then later convolving with x3 of t. Okay. Okay, what we are doing here, there are three signals. First, we are convolving x2 of t with x3 of t, then later convolving with x1 of t. But here, first we are convolving x1 of t with x2 of t, then the result is convolved with x3 of t. In both the cases, finally we'll get the same answer. Next, shifting property. Shifting property. Say x1 of t convolution with x2 of t will give the new signal that we generally used to take y of t or something, some signal z of t. Okay, z of t. Suppose if I apply the shift only in any one of the signal, for example, in the second signal I am applying the shift, okay, capital T, shift of capital T towards right, then what will be the result? Okay, the result is also will be shifted by the value of capital T. Okay, that is the shifting property. Or otherwise, if I apply the shift in first signal and convolving with directly with the second signal, then also I will get the same result. Okay, already signal is there, x1 of t, x2 of t. You apply shift in any one of the signal, so that your result is also will be shifted by the same amount. Okay, suppose if the shift is applied on both the signal, for example, for x1 of t, I am applying the shift of t1. For x2 of t, I am applying the shift of t2. Now, what is the shift in the resultant signal? That is t minus t1 minus t2. Okay, it's t2. Suppose instead of the right-sided shift, suppose if left-sided shift is there, for example, it is like this. Okay, both are left-sided shift, then the result is also will be left-sided shift. Okay, it's again it may be combination of right-sided shift and also a left-sided shift. Okay, say for example, if the situation is like this, then z of t minus t1 plus t2. Okay, it's very simple. Okay, whatever shift is there, that you just write it in the result. That's it. Okay, if shift is not there, you just write only this shift. If there are both the shift, then you just write that shift. Yeah. Okay, so that is the shifting property. Fifth property, convolution with impulse. Convolution with impulse. Okay, x of t convolution with impulse signal del t is same as x of t only. That means any signal convolved with the impulse will give you that signal only. Okay, will give you the signal x of t. Okay, next, convolution with shifted impulse. Convolution with shifted impulse. Suppose signal is there x of t, instead of direct impulse, delayed impulse is there. Okay, shifted impulse, delayed impulse. Then what is the result? The result is also will be delayed. Okay. Okay, what is the simple proof here? See, x of t is there. Then this is del of, suppose if it is del t, then definitely this is x of t. Okay. It is something like x of t convolution with del t gives some new signal z of t, but that z of t is same as now x of t. So now if you apply the shift in impulse, that means del of t minus t, again the result is also will be delayed by that factor, that is z of t minus t. But in our case, what is z of t minus t? It is same as x of t. So x of t minus t. Okay, so that's why x of t convolved with del of t minus tau means again the signal will be delayed by that amount, x of t minus tau t. So small t minus capital T. Next, convolution with unit step. Convolution with unit step. Convolution with unit step. X of t convolution with u of t is same as minus integral to t x of tau d tau, x of tau d tau. Okay, the same formula that we have already used in Fourier transform. Okay, to find out the Fourier transform for the unit step signal, we have used this formula. Okay, already in the previous classes. Okay, so x of t convolved with u of t is same as integral minus infinite to t x of tau d tau. Okay, next, convolution with shifted unit step. Convolution with shifted unit step. Okay, so x of t convolution with u of t minus t naught is same as minus infinite to t minus t naught x of tau d tau. Okay, again wherever t is there, just replace with the t minus t naught. Okay, extra shift. That shift you also provide here also. Okay, so next property is width property. Next property is width property. Suppose x1 of t signal is having the duration signal width. Okay, we are calling it as a t1. Say for example, if I have a x of t like this from 0 to t1, then what is the signal width? Signal duration t1. Okay. Similarly, I am having another signal with some other duration. Say for example t2. Then what is the result of this convolution width? Okay, see, then x1 of t I am convolving with x2 of t, then later I am getting one new signal, that is y2 of t. That means individually x1 of t is having width t1, x2 of t is having t2. Then what will be the width of output, that is y of t, that is t1 plus t2, t1 plus t2. Okay. So now question, given input x of t is equal to u of t and h of t equal to del of t minus 1, then find the response y of t. Find response y of t. Solution: y of t is equal to x of t convolution with h of t. Okay, x of t in this case is u of t convolution with del of t minus 1. Okay, and what is the result? Okay, if it is del t, this is simply ut, but this is del t minus 1, so that the result is u of t minus 1. Result is u of t minus 1. Okay, next question. Convolve the signal u of t minus 1 and del of t minus 1. Solution: the output y of t is equal to x of t convolution with h of t. X of t is u of t minus 1 convolution with del of t minus 1. Again, u of t convolution with del t is u of t only, but with this shift and also this shift. Okay, so that is u of t minus 2. Okay, y of t is equal to u of t minus 2. Okay, so the next topic is impulse response of the interconnected system. Impulse response of interconnected system. Interconnected system. In general, the two system may be connected in two different format. One is with the serial combination and another one is with the parallel combination. Serial combination and a parallel combination. Suppose if the systems are connected in parallel, there are two different systems, but that is connected in parallel. And the first system is having the transfer function, that is impulse response h1 of t. The second system is having transfer function or impulse response, that is h2 of t. Okay, now we provide same input to both the system, that is input is x of t, and then we combine. Okay, now we combine the output from h1 of output from first system and also from the second system. Then we take it as a single output, that is y of t. Okay, that is y of t. So now, again, whether they mention here or not, it is like here some summation operation is there. Whether they mention or not, okay, here summation operation is there. That means output of first system and second system will be combined here. Then that will be taken as a single output. Okay, so now, again, say for example, output of this one, I will call it as a y1 of t. Output of the first system, output of the second system, I will call it as a y2 of t. Then y of t is equal to y1 of t plus y2 of t. y2 of t. Now, what is y1 of t? y1 of t is x of t convolution with h1 of t. Okay, x of t convolution with h1 of t. Then what is y2 of t? X of t convolution with h2 of t. Okay, x of t convolution with h2 of t. Now, here x of t is common, that we can take out. Once if we take x of t common outside, then you will be getting h1 of t. Okay, then h2 of t. Okay, h2 of t. Okay, so now y of t is equal to x of t convolution with h1 of t plus h2 of t. Okay, so now this equation is denoting the overall system. Okay, now x of t is the input, and I'll call this as a h of t. H of t is the overall impulse response of the system. Okay, then I am getting overall output. Now the overall impulse response of the system, that I can write like h of t is equal to h1 of t plus h2 of t. Okay, I can write like this. Okay, in time domain. So now what will happen? I can also write it in the s domain, so that h of s is equal to h1 of s plus h2 of s. Okay, So now when the system is given in parallel combination, okay, then what is the effective impulse response or system transfer function? Means we have to simply add those two impulse response or those two transfer function of the system. Okay. Next, systems connected in cascade. System in cascade. Cascade means output of one system will be given to the other system as a input. That is the cascaded connection. Okay, now there are two systems, one with impulse response h1 of t and another one with impulse response h2 of t. For the first system, I am giving x of t as the input. Okay, now I'll get some output. That output is given as input to the second system. What is the output of this system? First system, that is y1 of t, but that is same as x2 of t. Okay, the input to the second system. Then I'll be getting here y of t. Okay, I'll be getting here y of t. So now what is the relationship between x of t and y of t? Okay, then so that I'll get the overall impulse response of the system. Okay, from this, what is y1 of t? Y1 of t is equal to x of t convolution with h1 of t. What is y2 of t? Y2 of t is equal to x2 of t. Again, this y2 of t is same as y of t. Okay, the output of the second system is same as the output of the overall system. Okay, so that I will write this as y of t. So y of t means y2 of t, that is h2 of t convolution with x2 of t. Okay, then h2 of t, what is the convolution? What is x2 of t? That is same as y1 of t. So y1 of t already we have calculated this. I will substitute here. So h2 of t convolution with x of t convolution with h1t. So just by rearranging, I can write like this: x of t convolution with h1 of t convolution with h2 of t. Okay, so this is the overall output. Okay, this is input part, this is system response part. This I can write like x of t convolution with a single impulse response, that is h of t. So that means what is the overall impulse response of the system? That is h of t is equal to h1 of t convolution with h2 of t. You see, instead of putting separate system like this, I can put the system, common system h of t, but that system has to satisfy this property. So that system has to give these values, okay, the convolution values, okay, so that I can use as a single system. Okay, then in S domain, we can write like h of s is equal to h1s multiplied with h2s. Okay, I am applying the convolution property. Okay, if convolution there in time domain, in frequency domain, it will be like multiplication. Okay, okay, so next, properties of impulse response of the system. Properties of impulse response of system. Properties of impulse response of system. We know that the system is purely defined by the impulse response. Okay, for example, I'm having a system here. Okay, I'm going to give some input and I'll get some output y of t, but that output is decided by the system transfer function or impulse response, that is h of t. Okay, so again, depending on the input and impulse response, I'll be getting some output. Okay, once if you keep h of t as a fixed value, okay, then if you change input, then output also will change. Okay, so that means the system characteristics is defined by h of t. System characteristics is defined by h of t. So then once if you know the nature of h of t, then we can say the nature of the system. What is the properties of the system, whether the system is stable or unstable, or it is causal or non-causal. Okay, we can tell easily by observing h of t nature. Okay, then the first one is causality. First one is causality properties of the system. That means whether the given system is causal or non-causal system. Okay, suppose if the system is defined only for positive value, then that system is defined as a causal system. So that means what? H of t has to be 0 when t is less than 0. Okay, then h of t could be anything when t is greater than 0. But definitely it has to be 0 when t is less than 0. Okay, so once if h of t satisfies this property, then the given system is causal. If h of t is 0 when time is less than 0, then that system is causal system, because we cannot operate on system at negative time. We cannot operate on the system at a negative time. So that if h of t is defined for negative value, okay, then that system is non-causal. That system is non-causal. Say, for example, if they are defining some system like this, h of t is equal to e power minus 2t u of minus t. If they are defining like this, then definitely this is non-causal, because the system is defined at negative time, so that the given system is non-causal system. Given system is non-causal system. Or otherwise, suppose if they are defining the system like this, h of t is equal to e power minus 2t u of t, then definitely this is causal system, because it has been defined only for positive time. Okay, because u of t means positive time from 0 to infinite, so that this system is causal system. Okay, then what about the stability of the system? Stability of the system. Stability. Okay, so now we have h of t, that is impulse response of the system. Okay, already we know that for a system, if we provide bounded input, if you provide bounded input, okay, then if you get bounded output, then the given system is stable. Okay, if the given system is stable, only then when you provide bounded input, then we will be getting bounded output. If the system is not stable, even though you provide bounded input, you may be getting unbounded output. Okay, it's because mainly the system is unstable. But whenever, to satisfy the stability properties, bounded input should produce bounded output, then we say that system is stable. Why? Because that we can easily understand from the area properties of the system. Okay, we know that the area property ax into ah is equal to ay. Okay, when area of x of t bounded means what? The area under that signal is finite. Okay, so if the input signal is bounded, that means it will have finite area, definitely some area, some finite area. And again, what should be the value of area of under ah, so that I will get again finite area here, some finite area. Okay, finite area here, also finite area. So finite area multiplied with what will get finite area. Okay, finite area, definitely this should also be a finite area. Okay, this should also be a finite area. So that means what? The area under the impulse response h of t has to be finite. Okay, so for the systems to be stable, what is the condition? Area minus infinite to plus infinite h of tau d tau should be less than infinite. Okay, the area under the signal impulse response h of t must be finite. Okay, so sometime they used to put modulus value here, no problem, because to overcome that negative positive, because magnitude, just magnitude we need. Okay, it may be negative also, so because we are telling less than infinite. Okay, so just modulus value. So the area under that signal, the area under the response h of t has to be finite, and the given system is stable. If you are not getting area as finite, okay, say for example infinite, okay, if it is not absolutely summable, okay, absolutely integrable, then the given system is unstable. Given system is unstable. Okay. Then few questions based on this. Check causality of the system. Check causality of system. Is h of t is equal to e power minus t u of t. Okay, definitely this system is causal system because h of t is defined in positive side. Okay, defined only in positive side of time, positive side of time. That is h of t is 0 when t is less than 0. That's why this system is causal system. This system is causal system. Then next question, find causality and stability, find causality and stability nature of system. That is h of t, h of t is equal to h of t is equal to e power minus 2t u of t minus 1 is solution. Again, if you see here, this system is also defined only at positive time. Okay, if you draw this one, okay, will start at t is equal to 1, then it will decrease gradually. Okay, now also the system is defined only at a positive time, that is h of t is equal to 0 when t is less than 0. Okay, so the given system is causal. Okay, then what about the stability? For that stability, we have to find out the integral from minus infinite to plus infinite, h of tau d tau. Okay, in integral minus infinite to plus infinite, e power minus 2 tau. Okay, what is that? E power minus 2 tau d tau. Again, integral varies from 1 to infinite. Limit varies from 1 to infinite. E power minus 2 tau d tau minus 1 by 2 e power minus 2 tau infinite 1. Okay, minus 1 by 2, 0 minus 1, not minus 1, 0 minus e power minus 2, e power minus 2. So finally we are getting 1 by 2 e power minus 2. Again, this is finite value only. Okay, if you substitute e power minus 2, you will be getting some number. And finally number only. Even if you divide by 2, finally this is number finite. Okay, so integral minus infinite to plus infinite h of tau d tau is less than infinite. Okay, less than infinite. So the given system is stable system. Given system is stable system. Okay, thank you.